Hi everyone, welcome to this video. This time we will be doing another problem on the quantum harmonic oscillator. This problem was also taken from Griffiths Introduction to Quantum Mechanics 3rd edition, and it is problem 2.13. Now this problem asks us to normalize the first excited state of the quantum harmonic oscillator that we found in a previous video. It is the wave function is given here, and we have to do this by direct integration. Then we want to check our answer against the general formula that we found using in the previous video, right, where we found this formula that we show here. Okay, so let's just do that. So part A, we just have to do this integration from minus infinity to infinity of the wave function. So that's going to be psi1 conjugate. So that's going to be minus I a1 omega square root of 2m x e to the minus m omega 2h bar x squared, and now times the same thing but not conjugate. So I'm just going to go ahead and write it out quickly. E to the minus m omega 2h bar x squared dx. Okay, so some things we can see right away. This I right here will cancel out with this, and they will leave a minus behind, which will turn this other minus into a plus, so that can go away. Now there's an omega on both sides, so this is going to be squared. The a1 will be squared. This term, the square root, will also be squared. The x will be squared, and this will get a 2 in here, so that 2 will cancel out the 2 that is in the denominator. So what we will be left with is just that right there, dx. So let us now take all the constants out of the integral, so we get a1 squared omega squared times 2m integral from minus infinity to infinity of x squared e to the minus m omega h bar x squared dx. So how do we solve this integral? Now this integral comes up very often, both in quantum mechanics and in statistical mechanics, and probably in other places too. So it's very important that you know how to solve it. If you don't, then pay close attention, because I really suggest that you learn this. So this integral may not be known right away, and the problem is that we have this x squared here. It's always good to think about what is the thing that is not allowing me to solve this. So in this case, it's that dumb x squared in front. So how can we get rid of it? So let's think, what if we had, so this integral is basically an integral of the form minus infinity to infinity x squared e to the minus beta x squared dx, right? So let us now think, what if we were to derive e to the minus beta x squared with respect to beta? Well, in that case, we would get minus x squared e to the minus beta x squared, which is exactly what we have in here, but this time it doesn't have the x squared, so we could actually use the fact that this would be a Gaussian integral, and we would get the result right away. So let us multiply each side here by minus 1, so we get that minus this derivative is what we have inside of the integral. So let us now rewrite our integral. Let's just call this I1. I'm going to leave the constant outside for now, so I don't have to be writing them all the time. So that integral I1 is going to be integral from minus infinity to infinity of minus the derivative with respect to beta of the exponential minus beta x squared dx. Okay, beta in this case is just m omega divided by h bar. Okay, this right here is our beta. So now we can just change the order of the integral and the derivative, because they are with respect to different constants, variables, sorry. Okay, so the minus is outside as well, minus infinity to infinity. And this, we know, this is just the square root of pi divided by beta, right? We saw that in the previous video. So this is d by d beta, square root of pi divided by beta. And well, now we have to actually take the derivative. So let's now put the square root of pi over here. I always like to, when I have to derive something that is inside a square root, I like to write it in the form just of a polynomial, like minus 1/2. this to the minus 1/2 power. I think it's just easier to integrate, to derive, and to integrate. Okay, so this is going to be minus square root of pi, and when we do this derivative, we get times minus 1/2, and this is going to be beta to the minus 3 divided by 2 power. So now the minus signs will cancel out. We get square root of pi divided by 2. And now we can just replace this beta by its actual value, which is just m omega divided by h bar. And this whole thing is to the minus 3 divided by 2 power. But we can also just flip this so that the exponential becomes positive. Okay, so this is going to be now h bar divided by m omega. So this is the value of the integral I1. So I'm just going to get rid of this whole thing. If you want to watch it again, you can always just pause the video and go back. So this is our integral I1. So let us now put it back into our original. I want to use a white color. Oh, there we go. Let us go back into our original integral. So that is going to be A1 squared omega squared to m times what we just found, which is just going to be square root of pi divided by 2 times, I'm going to write this in a kind of clever way, just h bar times h bar to 1/2, just so that it's easier to see what I want to do next. This to the first power times m omega 1/2. Okay, so now what we have here, we got this 2 will cancel out this, the omega squared will cancel this omega here, this m will cancel out this m, and we can take this h bar to be out here. So what we get is that a1 squared h bar omega, is that it? Yeah, so, and this, oh, my dog is going crazy. Okay, this multiplied by h bar omega divided by h bar pi. Okay, so h bar pi divided by m omega to the 1/2 power. Okay, so this is what we get here, and this has to be equal to 1. So from this, well, I'm just going to go to the next page. I don't really want to get my slide here too messy. So from here we can immediately see that a1 is going to be m omega divided by h bar over pi, and since we now have to take the square root because this is a1 and not a1 squared, this is going to be to the 1/4 power times 1 divided by the square root of h bar divided by omega. So this is our result using direct integration. This is the constant of integration to normalize the first excited state of the quantum harmonic oscillator. Now let us check it against what we would get. Oh, there's a car going outside, okay. Against what we would get using this formula right here. So I'm just going to write it here so that we can see the formula. So A1, according to it, is just going to be m omega divided by pi h bar to the 1/4 power times 1 divided by the square root of n factorial, which is just going to be 1 factorial, so 1, times h bar omega to the first power. So just this. So as we can see, it's exactly the same as we found, which is what we expected. So that is the first part of this problem. Now the second part asks us to find the second excited state and tells us not to bother normalizing it. Okay, so how can we find the second excited state? As we know, the second excited state is going to be some constant of integration a2, which we could find using what we saw in the previous video, but since it's not really asked of us, there's no need, times the this raising operator psi 1. Okay, so that's what we have to do. Now we have to write in here both this a plus operator, which is just h bar divided by I d by dx plus I m omega x, and psi 1, which I think was I times this constant a1, which we already found, ia1 square root of 2m omega x. I'm really pushing it here. I hope I'm remembering this right. I'm going to double check anyways. Let's see. ia1 square root of 2m. Oh, did I put the omega in there? I think I did, right? Yeah. Okay. ia1 omega 2mx. Okay, I think I got it. Great. So, well, now we just have to do this operation. It's just some algebra here. So we get, let us take all these constants out. So a2 times I times this a1 square root of 2m omega. And now we can actually start doing this. So h bar divided by I times the derivative of this. So it's going to be the derivative of the first, which is just x, times the second term, which is just the exponential, 2h bar x squared, plus, this time it's going to be x, times the derivative of this, which is just going to be minus 2m omega x divided by 2h bar times the exponential, 2h bar x squared, and close the parentheses, and now we got this second term right here, which is going to be plus I m omega x squared e to the minus m omega 2h bar x squared. Okay, great. Yes, I got all parentheses closed. So now, well, we can simplify some things. So this 2 will cancel out this one. Here we will get this x squared. So I'm just going to go ahead and simplify that. So I'm going to copy this. And actually, something else we can do is put this I inside. Okay, so we can multiply it inside. It's going to cancel out the I that is in here. So we get h bar. And we can also factor out this exponential. So it's going to be 1 plus, well, actually minus, Control Z, there we go, minus m omega x squared divided by h bar. The exponential goes out, and then we have this term right here, but this I is going to turn, well, I dropped an I here, didn't I? I think I did. We had, yeah. No, it's fine, it's fine. It's because it's this I right here. Okay, everything is fine. I was supposed to close this. That's why I was confused. Okay, so then we have minus m omega x squared. Yeah, why do I feel I'm missing an h bar here? Oh no, it's fine. Okay. And times e to the minus m omega to h bar x squared. Okay, there we go. Sorry about the little hesitation there, but it's all going well. Okay, so now what we can do is just multiply this parenthesis here out. So what we get, I'm just going to be changing it here. It's going to be, the first term is just h bar, and in the second one, it's going to cancel out this denominator here. So we get minus m omega x squared and 2 times, so we can just put that 2 in front, minus 2 times this. And now we can just put this over here. And well, basically this is our result. We can try to make it look a little better. In fact, what the books usually do is they just take a square root of 2m. They just pull the h bar out of here. So you get h bar omega 1 minus 2m omega x squared divided by h bar e to the minus m omega divided by 2 h bar x squared. And you can just absorb a1 into the a2 constant here. So this is the wave function that we were looking for. Okay, so since we don't have to normalize it, there we go. If we wanted to normalize it, we could just have left this a1 here, put in its value, and then we could have used what we learned before in the previous video, that when a plus acts on psi1, you get not just psi2, but I don't have enough space there, but the square root of n plus 1 h bar omega times psi2. So 1 over this would be our constant a2. Okay, so that is what we could have done there in order to find the constant of integration, but it wasn't required in this particular case. So the final part of this question is to check the orthogonality of the first of the ground state and the first two excited states. And as a hint, they tell us to exploit the evenness and oddness of the functions so that we can avoid some of the integrals. So the way to do this, and this is also why I wanted to show this problem, because I think it's really important that you are thinking about what these wave functions are. So we saw the psi0 is basically e to the minus something x squared. Okay, so this is an even function. Psi1 is going to be x times e to the minus something, well, something times x squared. So this is an odd function, right? And then psi2, we just found it. It's on one hand just the exponential, and on the other hand x squared times the exponential. So it is also, psi2 is also even. Okay, so why is this important? I'm just going to now write it as the following. It's very useful if you can know which functions are odd and which functions are even, because when you're integrating over symmetric intervals, odd functions will be 0. Okay, that is super important, and that is very useful. So let us now check psi0 inner product with psi1. Okay, this is the same, by the way, as psi1, psi0. Okay, because they are still going to be orthogonal, it's going to be the same. So the inner product will be the same. Okay, dx. So, well, since psi0 times psi1, this is even, this is odd, and an even function times an odd function will be an odd function. Okay, so, and you can easily check it because this is, as we said, e to the minus something x squared times e to the minus something x squared times x. So we are going to get still something to the x squared, but times x. And that is going to make it an odd function. And since our limits of integration are from minus infinity to infinity, which is, you know, a symmetric interval, this is just going to be 0. And that, remember, happens because in these odd functions, the graphs are usually something like this, for example, where this is not very symmetric, but it's basically the same on one side as on the other, but with opposite sign. So since in the integral you're kind of calculating the area under the curve, you know, kind of, depending on context, but that is what you're doing mathematically, that is going to be canceling out. Okay, so that is the principle. You can, obviously you are invited to do this integral explicitly if you are not convinced, and you will see that you will in fact get to this result. Now, on the same logic, the integral from minus infinity to infinity of psi2 and psi0 will also be 0 because this is even and psi1 is odd. So multiplying them will give you an odd function. So that's also going to be 0 in the symmetric interval. So just like that, easy as that, we already checked the orthogonality for psi0 and psi1 and psi2 and psi1. What there still is that we must check is the orthogonality of psi0 and psi2, because both of these are even functions. So their product is going to be even, which will not be 0 in this interval. At least not necessarily, not just because they are even. It might be some lucky coincidence, but it's not necessarily that. Okay, and by the way, we discussed when we were talking about the infinite square well that these wave functions were going to be orthogonal for basically everything that we were doing, and here you can see that is indeed that way. Okay, so let us do this. We now write in here our wave function. So psi0 is just the constant a0, sorry, times e to the minus m omega 2 h bar x squared. And psi2, we just found it. I don't really remember what it is. It was a2 square root of 2 over m h bar omega. Okay, I lied. I think I do remember it. Minus 2 m omega x squared divided by h bar e to the minus m omega 2 h bar. I think that was it. Let me just make sure. 1 minus 2m, I think that's what it is. It's a minus m. Yeah, okay, I think I got it right? Okay. So let us see. So we got these two exponentials that are going to be multiplying each other, so we can just get rid of one. I'm going to get rid of this one right here. Since everything here is just a scalar, it's going to be commuting, so I can just multiply them, put it in here. So we get 2 divided by 2, which is just 1, so it goes away. What else? Well, we can take these all these constants, so a0, a2, square root of 2 over m, h bar omega, all those things can just go outside, and we get the integral from minus infinity to infinity of just e to the minus m omega x squared divided by h bar, which is when we do this first multiplication. And then we get the second integral, so we get minus 2m omega divided by h bar, integral from minus infinity to infinity of x squared e to the minus m omega divided by h bar x squared dx. Okay, so we gotta solve these two integrals. The first one is quite easy. Okay, it comes from, it's just a Gaussian integral. The second one is this similar as what we saw before. I'm going to do it once again just to be thorough. So just this integral will be I2. So this is going to be then d by d beta, following obviously this here beta, minus d by d beta, integral from minus infinity to infinity of x squared e to the minus beta x squared dx. So this integral, oh sorry, this is not supposed to have that because we already did this substitution. Okay, so now this is just going to be minus d by d beta of the square root of pi times beta to the minus a half. Now we do this derivation, we get square root of pi divided by 2 times beta to the minus 3 divided by 2, but beta is just m omega h bar, so we can write it as h bar divided by m omega to the 3/2 power. Okay, so let us now go to the next page. So this integral is going to be all of those constants at the beginning, which I will just call alpha because they are not relevant in this case. I mean all these here, that's just, I'm just going to call it alpha. And then we got this first integral, which is just going to be the square root of pi divided by what is in here. So, I mean, we already solved those kinds of integrals. We talked about it in the previous video, so I hope there's nothing new there. Square root of pi h bar m omega minus, now the constant that we're in front of the integral, which is just 2m omega divided by h bar. Now times what we got here. So we got square root of pi divided by 2 times, I think it was, let me just check, I already forgot, h bar m omega 3 divided by 2. Okay. So this will just be this alpha, this square root is still going to be the same, h bar m omega. And what do we get here? So these constant multiplying here will just cancel out some of this, so you will be only left with 1/2 power. It's basically going to cancel out the 3 and turn it into the 1, right? So we are just going to get, and this 2 will cancel out this 2. So we're just going to get pi h bar divided by m omega inside the square root. So this is just going to be 0, which is exactly what we expected, because this integral was just basically the inner product between two states that are orthogonal to each other. So it had to be 0, right? Because remember this is supposed to be whoops, not an x, the delta and m, right? If we have two different states, in this case it's 0, 2, so we expected this to be 0. Okay, so that is this problem. I hope you understood everything clearly. If not, just let me know in the comment section. I will reply to any question I see if I have the time, and I'll see you in the next video.